Welcome to Study Loop.
Let's say that you took some data for the magnetic field as you move your magnetic sensor further away from a thick cable. So over on the left, I show that there are measurements of magnetic field in Tesla versus distance from the cable in meters. And a couple things to point out is, first of all, the measurements were made from the surface of the cable, meaning that you measured the distance from um, the outer edge of the cable. The other thing to keep in mind is that if you use Ampere's law, the magnetic field of a wire or a cylinder, very long wire or cylinder, is given by Ampere's law. And a reminder of that is that the B should be equal to mu naught over 2 pi r times the enclosed current. Now, what's important to note is R should be measured from the center of the wire. But for various reasons, this person measured from the surface of the wire. And the question is, ordinarily, if you rearrange Ampere's law, just simply rearrange it with the 2 pi r together with the B, and maybe put the mu naught with the 2 pi. What you notice is that the product of B times distance should be equal to a constant. And so the first thing to check is whether that's true for these measurements. So the third column shown there is the product of the previous two columns. Is it constant? And you can see that no, it is not. And there is a definite divergence from a constant. There is a pattern to it. It isn't just noise. So I am going to suggest that the problem is that the X should have been measured from the center. And that is why that constant is not occurring in that column. Okay, so what to do about it? Let's say you go home and you start looking at your data. You're like, oops, I should have done this other measurement. Well, not a big deal, because what we can say is that little r in the Ampere's law can now be rewritten as x plus what to call it, the radius of the cable. Let's call it r, big R. And if you now rearrange Ampere's law with this added feature, so let's just go ahead and sub this into Ampere's law. What we find after rearranging a little bit is that x plus r is equal to mu naught over 2 pi times I enclosed over B. And if we rearrange that a little bit more, what we can then see is that x as a function of the magnetic field should look like an inverse proportion. And if we pull the r to the other side, let me just kind of suggestively write this. And I'll put the 1 over b. And of course, there's a minus the radius. So if we take our data of X and magnetic field and we plot X versus 1 over b, we should see a straight line with the slope equal to all this stuff in front of 1 over b, and the intercept as a negative radius of the cable. So let's go ahead and plot the data. Again, I'm making sure that my X is in meters and my magnetic field is in Tesla. And indeed, if I make that line, it is a very straight line. And there is a slope. Of 1 times 10 to the minus 5 units of meters times Tesla. And the y-intercept is minus, let's call it 0.012. And that should be in meters. So we could immediately read off the radius of the cable. Okay, so that one was the easy one. From the slope, since it involves the enclosed current and the cluster of constants, 2 pi over mu naught times the slope gives us the current. And mu naught, a reminder about that, mu naught is simply the permeability of free space, 4 pi times 10 to the minus 7 Tesla times meter per amp. And so the other nice feature that we can get from this is what the enclosed current is, which is, of course, the current in the cable. And we get roughly 50 amps. So some nice things were obtained from this data, even though the measurements did not start out on the correct footing.